In this video, we're going to talk probability fundamentals here. We're going to talk some terms and definitions, make sure to clarify our points here. Then we're going to do some fundamental basic probability and evaluating certain events. Now look, this is just our building block here. In future sections, we'll get more tools to add to our arsenal to be able to evaluate and conquer larger experiments. Let's dive in. So first, what is the definition when we talk about probability? What do we mean by probability? It's really just a likelihood. Look, how likely do we think something's going to happen? And these probabilities usually range from 0 to 100. And if you talk about percents, maybe that's something like 0%. That ain't going to happen. All the way to something like 100%. Hey, look, that's a sure thing. As a decimal, something like 34% or 0.34 might be a good example. Now look, probability is absolutely necessary for understanding really a lot of these inferential statistics that we'll talk about in the future. If I take a sample and I project it onto a population, it's important that I understand that there's not a one-to-one. It's not exact. That sample represents perfectly the population. There's some wiggle room in there. So we need to be able to define how likely these things are tied to each other. We need to talk about probability. Now look, there are lots of origin stories as to where probability began. A lot of different studies that kind of built up what we have today. But one fun origin story, if we talk about the 1600s, or if you want to talk about the 17th century, right? Many ways to mention these things. There were some mathematicians that had a conundrum that they were trying to tackle. And this is a fun little situation. In fact, it's not in this video, but certainly in the future, we'll have tools to evaluate this game. Let me get into it. So there's a game consists of throwing a pair of dice 24 times. And so you take those two dice, you throw them, you look at the result. You pick them up, you throw them again. In fact, you do that again 24 times. And the wager or the game is whether you should bet or not that one of those rolls will come up double sixes, at least one. And so many of you might think about, okay, how are we going to tackle this? There's actually some fundamental rules or some tactics that we'll give in the future that will help this problem become a relatively easy one to evaluate. But before that time, let's build up some fundamental terms. Let me see if I can slide over here. That's a little better. All right. So the first term that we have is an experiment. This word experiment or trial oftentimes is just that situation that we're reading. That one's experiment's not too important. Instead, one that I'll highlight here that comes up quite a bit more often is outcome. This is a sample point that we're interested in. For instance, if my experiment was just flipping a coin. Let's say one coin, one time, that's all I was interested in. Then an outcome might be heads, or maybe the outcome might be tails. In fact, for one coin, those are the only two results. So the sample space, this is another one I'll highlight 2 times, super important. Sample space, the space refers to, look, this is everything in the whole wide world, everything that you could possibly imagine. In which case, for my little example here, here's the space. Heads and tails, that's everything that we can imagine happening. And then so all an event is just a collection of sample points or outcomes. And so maybe I'm interested in heads or tails or so on, and we can collect these outcomes together. But these are the 2 building blocks, outcomes or sample points and sample spaces. Those are the 2 building blocks. I'm covering up a little bit, so let me bend down. If you look above, I give you a sample of all these kind of words put together and also some examples, but we'll actually get into some of the examples. So if you want to pause the video and read them, you're more than welcome to do so. Let me dive right into our first example. There we go. Determine the sample spaces for the following experiments. And the question is, how many sample points or outcomes are there? So let's figure out what these spaces are and then get their count correct. The first one is just rolling a 6-sided die. What does that outcome or what does that sample space look like? Well, again, the space just comes from the collection of outcomes. And so let's figure out what those outcomes would be. I could get, for a 6-sided die, I get a 1, maybe a 2, maybe a 3, a 4. You see the way this game is being played. In fact, these are all the different outcomes that exist. And so this makes up the whole space. You can count these, or we can look at them and see that the count is just 6. That's the size of my space. Little side note for you, a little bonus tip here. Notice we're using capital N. Lowercase n always represents a sample, meaning that we're talking about sum. But we're not talking about sum. These are all population, the whole game, everything that can possibly happen when we're rolling a single die one time. Let's check out part B. I want to flip a fair coin 3 times and record the result in order. So order matters here. We should be looking at this again. Think of just one outcome, and then we'll build it from there. So I'll start with a nice one. Let's write heads. I get heads and heads again, and that's one outcome. That's going to help build up our space. Well, there's no ways I can manipulate or reorder these things, and so let me introduce a tail. I'll write heads, heads, tails. That's a different outcome now. I notice order is very particular here, so if I move that tail and I switch it with this head, I'll end up with a different event. Heads, tails, heads. And look at that, I have a different event. It's still one tail, but it's a different order. Let me take that tail again and shift it over to the left again. I'll end up with tails, heads, heads. With this method of doing this swapping method, I'll get all the permutations is the buzzword that we're interested in, but I'll get all the orderings of my one tail flipping a coin 3 times. And so that's why I stress that method of just simply swapping a few of them. But I've exhausted them. So now let me come back over here and write heads, tails, tails. Now, depending on your reordering, I can't take this tails and swap it because I'll end up with the exact same thing. And so instead, let me take this head and move it through. So I'll end up with tails, heads, tails. Let me swap the head one more time. I'll end up with tails, tails, heads. And now I've gone through all the orderings with 2 tails. And so now we're thinking, what's the last possible outcome that I can end up with? I have 3 heads all the way at the top, 2 heads, 1 heads. The last outcome, and this may be quick to you, may not be, is no heads. That's all tails. And so we can group them in this way. And if we think this is all the possible outcomes, this makes up the space. My space in this case is 8. And this is how we build up these spaces. Again, in order to find probability, we first need to figure out what the space is. Once we figure out the space, then we can actually start talking about probability. Good, I'm going to shift my weight over here. This is a little better. So assume that all outcomes in the sample space are equally likely. This is an assumption that we'll make throughout really most of chapter 3. Well, E is some event. We'll give it a name. And what we're really interested in is this new terminology, or this way to write these probabilities out. It's read right here, the probability that E occurs, or a way that you might also read it is this P stands for probability. I'll abbreviate it. These little parentheses stand for of, and that's my event E. So it's the probability of E, or the probability that E occurs. And this is how we can understand or notate our probability. It's a shorthand, if you will. And we can find this probability by simply looking up top. This is the number of outcomes in E, or this is like what we're interested in, and then divided by the space. This is exactly what we counted before. And so really when I look at my probability, I can evaluate it by just looking at the frequency, that's what F stands for, divided by N, my space. Or another way to write this is just the number that I want up top divided by how big my space is, the number of my space down below. And so with that in mind, with this idea of everything being equally likely to occur, let's dive in and evaluate some probability. Assume that a fair coin is flipped 3 times. Find the probability of the following events. The beauty of this question is it relates right to the sample space that we built before. Here it is. That was all heads, heads, tails, and so on down the line. This is the whole space that we could possibly imagine. Let me duck down a little bit. The first part is getting exactly 2 heads. And so the question is, how can I express that in my new notation? I wrote out a little bit of a starting block for us, and it's read, the probability of blank. What do we want to write here? Well, if you want to be super precise here, we can say of getting 2 heads, and I can write out the full event there. If you want to be a little bit more shorthand, maybe like, ugh, that's way too much writing, I can write 2H, something like this, right? The actual, what you write in there is not particular so long as it portrays the event that we're interested in. I think the most generic one is just to write, look, I want to get 2 heads in there. And then when we do our basic probabilities, everything being equally likely, we should just think, look, I need to count the number of outcomes that are what I want divided by the number of my space. And we can get these probabilities in mind. Again, I want exactly 2 heads. I can look over at my little sample space over here. Here's one. This outcome is what I want. 2 heads and a tail. Yep, that's exactly 2 heads. Down over here, heads, tails, heads. That's one's it as well. And then look at this one down below. These 3 events are exactly what I want. I don't want anything else because, again, I want exactly 2 heads. So, sorry, 3 heads does not fit that quota. And so when I look, the number that I want, I can write that as 3 divided by how big my space is. Again, you can count all those up. It should be 8. So that's my fraction. As a decimal, we can put this into a basic calculator. You can get 0.375, and that's exact, no rounding. But that's the probability that, again, if I flip a coin 3 times and I look at the result, what's the probability that in those 3 I'll have exactly 2 heads? Well, you can look. It's about a 37.5% chance. And that's no rounding. That's exact. All right, what about this next one? Let me move out of the way here. It says getting no heads. I don't want any heads whatsoever. Let's see what this looks like. I'll write it like this first. First, we'll write probability of getting, and I'll write here, no heads. We're not interested in getting a head. There's a lot of different ways that we can understand probability, but we need to start with the same fundamental probability of an event occurring. Now, one of the beauties, and we'll talk about this much more going forward, but we should be interested in understanding what does it mean no heads. Well, certainly there's different ways we can talk about this. We could think about that as the probability of getting, if I look over top, no, that one doesn't quite work for us. That's 3 heads. These are 2 heads. That's 1 head. Hey, you know what's the same thing as getting no heads? The same thing as the probability of getting all tails. You know, maybe we could get rid of the probability to be more exact, because these 2 events are exactly the same. I can simply write this as there's 1 all tails or no heads divided by my 8 in total. So my actual probability is 0.125. Not very likely, but certainly there's a decent chance. There are 12.5% chance. But it's this understanding that we can write these events, no heads is equivalent to, it's exactly the same as getting all tails. And so it's important that we kind of get comfortable writing this terminology, which is why we're introducing it here. 2 6-sided dice are rolled, 1 red and 1 blue, let's say, and the results are added together. And so, for instance, this first 1 sample point is you rolling a 1 and a 1. Of course, if you add those together, you'll get 2. And so 2 different ways to think about this, either as snake eyes, 2 1s, or the number 2. Here we go. Let's do another one. 3 and a 2 is the same thing as getting a 5. We're adding these things up together. So the big question that we're interested in is this the sample space for this experiment shown below, as we just talked about. In order to talk about probability, we need to understand the space. And so the question is, how large is the sample space? I'll write here, n equals blank. So if you want to, you could count up. Here's 1, 2, 3, 4, 5, and 6. All right, 6 over here, and you can count up 7, 8, 9. It's actually a fast way to do this. Looks like area. I have 6 going down, 6 rows. I can count the columns. 1, 2, 3, 4, 5, 6 over here as well. And so I can count this 6 times 6, my space. I have 36 different outcomes. 36 outcomes to speak of. And so this is going to help us. That's our bottom. That's our denominator when we talk about probability. So it's important that we tackle that one first. And then we can answer questions like this. Find the probability that the sum of the 2 dice is equal to 9. So again, first we got to express what that looks like. I'll write this as the probability, and I'll just write sum equals 9. Again, whatever's inside of here should just be the event. And there are many different ways to write it. This is only one. So I'll write here equals. Again, we're just getting started. I'll write, look, the number of outcomes that are what I want divided by my space. Fortunately for us, we've already answered that denominator, that bottom question. So I'll write here 36 on the bottom, beep, and the top number that I want. Sum is equal to 9. This is the beauty of having this table. It should be very friendly because, hey, look at that. The sum is equal to 9. It looks like if I get a 6 and a 3, yeah, perfect. That sum is 9. And if you'd like, you can search and search and search everywhere all over, but you're going to find this odd trend. It's a diagonal trend that if I get a 6 and a 3, that adds up to 9. If I get a 5 and a 4, hey, check that out. That also adds up to 9. And if I get a 4 and a 5, right, a different order, that's still the sum is equal to 9. If I go up again, 3 to 6, hey, look at that. It's 9. It's an interesting pattern that the sums go up diagonal over here. but I can count them. 1, 2, 3, 4. There are 4 outcomes that are what we're interested in. The sum is equal to 9. We can literally just count them. This is a decimal. I cheated. I did it beforehand. Should give you something like 0.1111 if we round to 4 decimals. You could box that decimal, and that is the likelihood or the probability. Again, probability, hopefully right now, a basic concept. We're looking at the number that I want divided by my space down below. And if you can divide those two, you're golden. You can tackle much probability. Here's another example using, again, just fundamental rules of probability, everything being equally likely. Let's say you make a New Year's resolution to stop playing video games for 1 month of the year, right? We're high stakes over here. You decide to pick a random day of the year and will avoid video games for that entire month. Okay, we're playing roulette over here. Over here, I have a calendar for our reference of all the days in each month. And we're not going to do leap year, so let's do 28 in February. So here's our question. What is the probability that you will avoid video games during January, that will avoid games? Well, really what that looks like, probability that we will outright avoid games during January, is the same thing as us finding the probability that we pick a day in January. Equals. And so I should always set up, whenever we're doing probability, number that I want up top divided by my space down below. Now, space refers to everything in the whole wide world that can possibly happen. If we're talking about a single day, well, then my space, well, that refers to all the possible days that are out there. What's out there? Well, there's 365 days to choose from. Maybe I don't want this, but certainly it's what we're interested in. Picking a day in January, we can see it up here. There are 31 days in January. If you divide 31 by 365, you'll get a decimal like 0.0849. And you can box that. That's the probability. Again, if you don't like decimals, if that doesn't quite connect to you, you can think about it in a percentage. That would be 8.49%. Again, move that decimal over 2 places, and that'll translate into a percent. Maybe that has more meaning for you. 8% or 8.5% likely. Not super likely, but certainly, again, still a chance out there. What if we want to play higher stakes? I'm like, look, I'd like to play games in January, February. Maybe I'm more like, hey, look, what's the probability that you will avoid games in the month past September? So I'm like, look, as long as I can hold off till then, I'll be golden. So what's the probability that we work in a month past September? You can look at my chart over here. So past September, I don't include it. October is satisfying. November, yes, and December as well. So I'll write this probability that we're in a month, all right, past September, I'll abbreviate here, equals, well, again, my space is not going to change down below. We're still interested in the 365 days, but I'm not just picking from 1 month. I'm picking from, look, 31 is good, plus 30 is good, plus 31 is good for October, November, and December. We can add those up, and in the numerator and the top, you'll end up with 92 divided by, that's still 365. If you write that as a decimal, you'll end up with 0.2521. And you can box that. That's the probability that we're interested in computing. Again, if you like the decimal or the percentage, you can write that as around 25%, about a quarter chance that if we were to avoid video games, the likelihood that we would be in a month past September, pretty likely, about a quarter. So certainly in the running there. These table examples describe one of the most common methods for computing probability, especially when we talk about basic rules. We have a nice chart organizing these different categories, and we're going to compute or pull probability from it. This table describes the distribution of a randomly sampled S of 100 individuals, organized by sex and whether they're right or left-handed. Compute the following probabilities. So this one, again, we don't have to be very verbose in our questions. We can simply say the probability M, which translates to the probability, a little parentheses just of, that we pick a male in this case, equals. Well, again, it should always be a nice little fraction, number that we want up top divided by our space down below. There's 2 different ways to do this. Let me show you the first. So if I look at males, well, here they are. These are the people that we're interested in. I have 43 and I have 9. I can add those up pretty quickly here, and I should get a number like 52 if I added up those males. The total, well, either I can look up at the question, it says there were 100 individuals in total, or if I wanted to, I could add those females up, 44 plus 4, and get 48, and end up with my total down over here of 100. And so that's my total, that's my space, that's what I'm pulling from. What's the probability that if I close my eyes and I pick at random, that I get a male? Well, there are 52 males out of the total 100 as a decimal. That should just be 0.52 around. If we wanted it as a percentage, that'd be 52%. So this is us getting more comfortable computing and pulling probability from a table. There's some other terminology that we'll get more into later, intersection and union. These words are just fancy words for and or. Let me demonstrate for you. This is the probability of male and left-handed. And this is the way we can read this. Again, I'll abbreviate male and left, give it some more meaning to us. So equals to probability. Well, again, my space doesn't change. You can write 100. You can get that one for free. That's my space. But now I want to know how many individuals are both male and left-handed. And so looking at my chart, let me erase my males over here. Certainly I have 43 and 9 males, but how many of the males are left-handed? It's just these individuals. There are 9 male and left-handed, because and signifies really that they need to be both at the same time. So the probability, again, you can use a basic calculator to compute, should be 0.09. You know what I'm thinking? Not very likely, but certainly on the board. All right, 0.099% chance male and left-handed. What about when we look at this technically a union or situation? Again, or is like, hey, look, anything goes. Either I can be male, and that works for us, or, either I can be male, or I can be left-handed. Either one is perfectly fine. Let me work down a little bit over here. My space, of course, remains the exact same. No worries. They're still dealing with the 100 individuals. But males, okay, if I want to look at my males, well, we've already done that. That's the 43 and the 9. In fact, I could add those up. For my males, I'll write an M over here. We had 52 of those individuals, plus I'm also interested in left-handed individuals. Now look, don't be fooled. If I add up my left-handed individuals, that's 9 and 4. That gives you a number like 13. But I don't want to write 13 here. We don't want 13 there, because if I did that, well, then I counted this 9 people twice. I counted them when I did the males and when I did the left-handed people. Counted them twice. And so I certainly don't want to write 13 there. Instead, what we should write is just those individuals which we didn't count. All right, 52 plus 4. There's also another formula that we'll talk about later that resolves this issue, but we'll leave it alone like this. I have my 52 males, that row, and then the 4 left-handed individuals that I missed. And so altogether, that should be 56 individuals that are doing what we want them to do, divided by the 100. This is a decimal, should be 0.56. And that's the probability that we get male or left-handed. And close our eyes, pick somebody at random. Now we're going to flip the script. We're going to introduce another term. I mentioned earlier that and or are just more common words for intersection and union. We're going to have a more common word for complement that we'll talk about here in a minute, but that word is not. So probability that we're not a male equals. This is much like our example of getting no heads that we talked about in the past. Not male. Well, again, you can look at your chart here. I only really have 2 rows here, male and female. And so by not male, I can cross them off. I don't want these individuals. So I'll cross them off. And it looks like these are what we want up top. Is this 44 plus 4 divided by my space, always the same, of 100. Or I can clean this up. 44 plus 4 is 48 divided by 100. As a decimal, that's 0.48. And we can get our probability. Oops, I'm in the way. 48 right there. And that's our probability of getting a not male. And we can see it from our chart. So again, we have this different language, intersection, union, and complement that we're skipping around, and, or, and not. Let me get into this not term here. Good. So when we think probability, a lot of different ranges here. Something either cannot occur, 0, look, this thing ain't happening, or 1, this thing is guaranteed to occur. And we're interested in these probability of events. But one thing that we need to consider does it look either something is going to happen or it isn't going to happen? That this is everything in the whole wide world. Something is or isn't going to happen. And so how do we define something as not occurring? It's like the not male that we talked about earlier. The phrasing that we're looking for, and I'll start because something that's important for us, is complement. The complement of an event A is denoted A, C. Little c up top denotes complement. Right? A to the C denotes complement, denotes opposite of that event occurring, not an A. Little example here from rolling dice is saying maybe what I want, what A is getting a 5 or a 6. So then complement is just everything that's not in A, which would be a 1, 2, 3, and a 4. A complement versus A. Sometimes you'll see this, again, very rarely is written as A prime, little A tick mark there, but that's pretty rare. I'll stick with A complement notation here. There's some very powerful formulas that come result. The first one is just one that I talked about earlier that look, either something is going to happen, this is that it happens, probability of E, or that it does not happen, right? Either something's going to happen or it's not going to happen, and there's nothing else in between. So if I add up these two events, if I add them up, well, then it's one. It's everything in the whole wide world. Either something is or isn't going to happen. If I add up those two probabilities, I should get one because that's everything. The beauty of this formula is if I simply subtract one of those parts, for instance, this probability V, if I subtract it over here, little minus sign, then I get this formula. Ooh, I'll start this one twice. This one's a really big deal. It says, look, the probability of E occurring is equal to 1, which represents everything in the whole wide world as far as probability is concerned, minus E complement, E not occurring. And really what this is like getting us out of a pickle. Sometimes E is very difficult to calculate. And so if I can think of the opposite event, well, then that might be an easier event to calculate. And so it's something that we can translate. So that's why 2 stars, it's certainly a nice tool to use. Let me give you an example. Here we go. The probability of flipping a coin 5 times in each flip, turning up heads, is 1 divided by 32. So that's 5 times. That's heads, 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 and heads. 1 divided by 32. What we're interested in is I want to find the probability of getting at least one tail. These two things might seem disjointed, but they are actually very related. So again, let me write out what we have. Find the probability of getting at least one tails. So probability of getting, all right, at least one tails, or at least one tail equals. So here's our pickle. If I want to get the probability of getting at least one tails, you have a little cheat sheet over here for us to reference. That would be getting 1 tails. That's what I want. But also at least 1 includes 2 tails. That's what I want. 3 tails. But that's also what I want. 4 tails. Okay, this is ballooning out of control. In fact, this at least 1 includes all of these different events. And so if I wanted to compute this at least 1 tails, I would need to find the probability of getting 1 tail, add it up with 2 tails, add it up with 3, and so on down the line. I have to find up and add up all these different events together. And look, if I'm flipping a coin 5 times, we can get to it on another day. My space is equal to capital N is 32. This is a large space. I have to write up all these different flipping of coins and add them all up. Okay, this is ballooning. It's getting way out of hand. And so instead there's a trick, a way to work around this thing. Let me change my color to red here. And that is to think of what I don't want. This is what I don't want. I want 1 tail, 2 tail, 3 tail, 4 tail, 5 tail, but I don't want no tails. That I can think about this as A, the event I want, and up top, this is a complement. Well, didn't we have that nice formula from before? I'll keep it in red. The formula said that the probability of A is equal to 1 minus the probability of A complement. And so if I'm going to work our at least 1 tails business, I can translate this formula to 1 minus the probability of the complement. The opposite of getting at least 1 tail is the probability of getting no tails. That's the opposite, at least 1 tail. That's the complement, no tails. And there's a really nice formula. I included it here on this slide for our reference. I'd encourage you to start, write it on a scrap sheet somewhere. a nice little cheat sheet to have in your back pocket is, look, the opposite of doing something, at least one, the opposite of that is doing none. So here's my little cheat sheet. Probability of at least one, think 1 minus probability of none. Sort of rhymes. So hopefully that makes it more friendly. So let's get into evaluating this probability. It should look like this. 1 minus the probability of getting. You remember in the beginning we talked about getting no heads. What's the opposite of getting no heads? This is like the reverse of that. Check it out. The probability of getting no tails, again, that's the event I want to calculate here. Well, instead of thinking about this as getting no tails, I can think about this as getting all heads. So, all right, all heads over here. Very fortunate, fortuitous of us, probably getting all heads, if I'm flipping a coin 5 times, is getting heads, 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 and heads. But actually, we know the probability of getting all heads. That's what they started the question off with, this 1 divided by 32. So the probability of getting all heads is 1 divided by 32. If you want to be fancy, you can do some fraction math, and this should be 31 divided by 32. Oops. This should be 31 divided by 32. As a decimal, it's going to be actually fairly likely 0.9688, which should make sense, right? The probability that we're interested in finding is, look, I just need to get one tail, at least one tail, which if I look at my space up above here in this little chart, it seems like there's a lot out there. 1 tail, 2 tail, 3 tail, 4 tail, 5 tail. These things are all good. In fact, the only thing I need to watch out for is getting no tails. And so, yeah, this is certainly very, very likely to occur. 96% chance. Again, if you like to think about this as a percentage, 96.88%. Very, very likely to occur. And complements help simplify the process. Last example. High school administers the ACT and SAT standardized tests to most of its students. It is known that 74% of the students took either the ACT or the SAT test. A student is selected at random. Find the probability that the student took neither test. This one's a goofy one. Let's dive right in. So I want to find the probability that somebody basically did nothing, that they did neither test equals. There's a good way to think about this, and it's going to be complements, but let me show you how complements come about. Really what this is the probability of somebody doing nothing. What's the probability that they avoided tests altogether? Well, one way to think about this is really like the opposite of my formula up above, is the likelihood that they do nothing is just 1 minus the probability that they did something. Probability of nothing is just 1, everything in the whole wide world, minus the probability that they did something. So if I want to translate that to our situation, probability that they did neither test will just be 1 minus probability that they took at least one test. At least one test. Here we go, equals 1 minus. Let me translate what that means. Probably they took at least one test. That means they took the AC test or they took the SAT. They took either one of those are perfectly fine. ACT, SAT, both are great. At least one test. That's exactly what this is. ACT or SAT. And it looks like we have a probability, 74%. That's a percentage though. Let me put it into a decimal. If I take this decimal right here, 74%, and I move it over 1, 2 to the left, I should get the probability of 0.74. Then I can subtract these two. As a decimal, that should be 0.26. And this is the probability that we're interested in computing. Let me wrap with this. So when we talk about probability, one of the fundamental rules that we should be thinking of is there should be a fraction at play. Before this complement stuff, there should always be a fraction at play. It should always be what I want up top divided by my space down below. If you can understand probability in that way, we're on our way to success. This rule of complements, this at least 1 minus none, is just the first tool in our arsenal. As the section progresses, we'll get more tools, more tricks to the trades, as it were. And so I'd encourage you to have these on a scrap sheet or to have them in your back pocket, and they'll certainly benefit you going forward. Let me end with this. If you appreciated the video, thank you for the time that you put into it. If you didn't, I apologize. For the rest of you, I'll see you in the next one.